This lecture is going to be over elements of Chapter 9 out of Con, where we're going to be looking at dose distribution and scatter analysis. So our goal is to try to figure out how we can determine what the dose is at a particular point in the patient. And we're going to try to position the patient such that we're either doing an isocentric treatment or we're doing an Ssd type of treatment. We need to be able to have reliable methods by which we can arrive at what we think that dose is. Now, many of the methodologies that we're going to go through over this particular chapter are for more simplistic situations. However, we're going to use these basic methods and we're going to derive more advanced methods from them, things that you might see used in the clinics today. But in order to be able to do that, we have to build on what we know. So we're going to take measurements in phantoms in order to be able to compute what these doses are. And we're going to use various methods here, such as percent depth dose, tissue error ratios, scatter error ratios, in order to be able to determine how that dose changes as it propagates from one spot in the patient on forward. So these traditionally were used for low energy beams, which were calibrated in terms of exposure rate in air or dose in free space. But the current methods, such as TPRs or TMRs, are better suited for high energy beams and involve measurements in phantoms rather than in air. So things are going to change a little bit, but they're built on the methodologies used for these particular methods when we would measure dose in air. Now, in phantoms here, we're going to take some material that's very, very close to water in terms of density, and we're going to make measurements from that. It is something that we can produce and that we can reproduce if necessary. Usually a water phantom is going to have problems with ion chambers and other detectors unless they're designed to be waterproof. So that's another reason why we go to this. Solid phantoms have been developed as substitutes for water to use with radiation detectors. For a given material to be tissue or water equivalent, it must have the same effective atomic number, number of electrons per gram, and the mass density. So with all of that being said, we need to be able to find some materials that fit that description. For megavoltage beams in the clinical range, we are looking at the Compton effect. And the necessary condition for water equivalence for these beams is to have the same electron density or the number of electrons per cubic centimeter as that of water. So how do we go about calculating the electron density? We can take the mass density, multiply by Avogadro's number, and then take Z and divide it by A. So we can then rearrange this particular or take this part of the formula, and we can take certain sections and multiply it by the density divided by the atomic number, or the atomic number divided by the atomic weight, sorry. And we can break it out such that we know on average about what this is. And the reason we want to be able to do that is because different parts of the human body have different tissues. And those tissues are going to have certain densities. The value of the electron densities for some tissues are going to be in listed in table 5.1. Obviously, this is not 5.1, but bone is going to be more dense than say something that is very, very close to water. muscle is going to be a little bit different from that. Fat is going to be a little bit different from that. So those different sections are going to change. In this table down here, we're going to have properties of various phantoms that are frequently used in radiation dosimetry. So you can see the waters or the material that are listed here and what the mass density, number of electrons, so on and so forth. And then you've got the photoelectric effect over here. Normally, we're going to be looking for something that is close to something called solid water, an epoxy resin-based mixture. It's a mass density that is 1, number of electrons is close to what we see here. So that's generally what we are going to be trying to use in order to be able to make our measurements. And there's our rando phantom right there, where we can get an idea as to how the radiation might behave in that particular phantom. So an anthropomorphic phantom. So now that we have the phantom itself, how do we go about making measurements? Well, this is where the techniques start to come into play. We're going to look at depth of dose distribution. So we've got a beam that's coming in on a patient or a phantom, and then the absorbed dose in the patient is going to vary with depth. The variation is going to depend on beam energy, depth, field size, distance from the source, beam collimation system. So the calculation of the dose in the patient involves considerations in regard to those parameters and others. So we're going to take the essential step in dose calculation system to establish depth dose variation along the central axis of the beam. And we're going to end up defining a number of quantities. We're going to have tissue error ratio. We're going to have TPRs. We're going to have TMRs. And these are usually going to be derived from measurements made in water phantoms using ionization chambers. And although the dosimetry systems such as TLDs and diodes and films are used occasionally, ion chambers are preferred because they have better precision and smaller energy dependence. So now let's go into the first method here that we're going to discuss. We're going to characterize the central axis dose distribution by normalizing dose at a depth with respect to the dose at a reference depth. So this quantity, a percentage or percent depth dose, PDD, is going to be defined as the quotient expressed as a percentage of the absorbed dose at any depth D to the absorbed dose at some reference depth, D sub 0 along the central axis of the beam. That is actually, let's see if we can blow this up a little bit. That is actually D naught. That's what it's referring to there. So again, this is something that was, this is a technique that probably came about more because of the using low energy units before we obviously get to the point where we're using the technology that we are today. So for ortho voltage up to about 400 kVp and low energy X-rays, the reference depth was usually at the surface. For higher energies, the reference depth is going to be taken at the peak absorbed dose or wherever it hits Dmax. And that's, depending on the energy, is going to occur deeper into the phantom here. And since the depth of peak absorbed dose for a given energy beam also depends on the field size, the reference depth should be determined for a small field size, such as a 3x3, to minimize electron contamination and be kept the same for all field sizes, irrespective of where that peak actually occurs. So in clinical practice, the peak absorbed dose on the central axis is sometimes going to be called the maximum dose, the dose maximum, given dose, or sometimes just simply Dmax. And therefore, if you take this particular formula and you interchange the positions here of those two items, then Dmax is going to be equal to the depth dose of interest divided by P, or your percent depth dose, times 100%. So the parameters that are going to affect this are going to be beam quality, energy, depth, field size, and the shape, source to surface distance, and the beam collimation. So now we're going to go through some of those quantities. So the PDD beyond the maximum dose, which is what you're seeing here in this particular graph, is going to decrease with depth. In other words, as you go further along, the percent that remains, the percent of dose that you see there, is going to be less than what you see at the peak. Now, higher energy beams are going to have greater penetrating power and deliver a higher percent depth dose at a given depth. In other words, you can see here the 25, it's decaying, but it's not decaying quite as rapidly as the 10 MV, or certainly the 4 MV or the cobalt 60. So it's really hanging in there. So the effects of the inverse square law and scattering are, if they are not considered, then the PDD variation with depth is governed approximately by the exponential attenuation. And you'll remember those exercises back in the fall of trying to figure out what percent of the beam was actually present at a given distance into the into whatever it was cutting through. So the beam quality affects the percentage depth dose by the virtue of the average attenuation coefficient. So as that decreases, then the beam becomes more penetrating, resulting in a higher PDD at any given depth beyond the buildup region. We'll get to the buildup region here in just a minute. Now, if you look at that particular figure, the PDD decreases with depth beyond the maximum dose. However, there's going to be an initial buildup of dose that becomes more and more pronounced as the energy is increased. And you can see that here. In other words, it's going to take time for those photons to get in and to start interacting with those atoms and start to knock electrons loose. And because it's going to take a little bit of time, as you go in a certain distance into the patient, you're going to see a lot of the percent depth dose start to build up as electrons start to impart their energy into whatever the medium is. And that region between the surface and the point of maximum dose is going to be your buildup region. Clinically, this is also referred to as the skin sparing effect. In other words, you can't get an automatic 60 gray dose at the skin unless you lay something over it in order to be able to build it up. Now, that has certain advantages because it allows the skin to remain intact while you're able to penetrate pretty far into the body in order to be able to deliver a certain dose. So for megavoltage beams, such as cobalt 60 and above, the surface dose is going to be much, much smaller than what it would be for an ortho voltage. One way to think of it is that you've got a high energy photon beam entering the patient. And so the high speed electrons are ejected from the surface and subsequent layers. Those electrons deposit their energy until they are stopped, which occurs at a significant distance downstream from their site of origin. Because you've got A and B going on, the electron fluence and hence the absorbed dose increase with depth until it hits a maximum. However, the photon energy fluence continuously decreases with depth, and as a result, the production of electrons also decreases with depth. And so the net effect is that beyond a certain depth, the dose eventually begins to decrease with depth. So now we're going to get to a concept here that is known as KERMA, kinetic energy released in the medium, or kinetic energy released per unit mass. And as we had talked about in chapter 8, if you remember back that far, K may be defined as the quotient of the change in the energy divided by the change in the mass. And that's going to be the sum of the initial kinetic energies of all of the charged ionizing particles liberated by uncharged ionizing particles. So you've got a small amount of mass, you've got the photons coming in, they're hitting and they're imparting energy to those ionized particles, and then they get liberated. So that's going to be your kinetic energy release in mass. If you look here at a graph, you've got the depth in whatever it is you're shooting at, and you've got energy that is listed over here, your KERMA, since that's defined as it's related to the unionized particles, or the photons coming in and delivering their energy into the patient. The KERMA is going to be maximum here at the surface. As those photons decrease, you're going to see a slower and slower, or a lower and lower amount of absorbed dose being introduced into the patient, or KERMA being active in the patient, I should say. For absorbed dose, however, you're going to see a buildup as those electrons are released. And obviously, all throughout the buildup region, this will eventually get to the point where it meets KERMA. And the rationale behind that is that once you get to the end of the range of the electrons, that's going to be the maximum point at which both your dose and your KERMA are going to, or your absorbed dose is going to meet KERMA. That's going to be the maximum amount of dose that can be deposited into that particular medium. After you get past the buildup region, or whatever that range is, then things start to decrease because you don't have as many electrons coming in and depositing dose. So you start to see a decline. Since your KERMA is pretty much limited by the photons that are going on, and your dose is related more to the energy, no matter whether it comes from photons interacting with electrons or just electrons that are being scattered through there, your absorbed dose is going to be a little bit higher. Now, the effect of a field size and shape. A field size can be specified either geometrically or dosimetrically. Geometric field size is going to be defined as the projection on a plane perpendicular to the beam axis of the distal end of the collimator as seen in the front center of the source. Think of a light field as it goes on to a patient, where, you know, or a phantom, better yet. You can see where that light, where those borders are clearly defined for a particular field. That is going to be considered more of your geometric field size. Now, the dosimetric, or the physical field size, is the distance intercepted by a given isodose curve, usually 50%, on a plane perpendicular to the beam axis. So in other words, if you have, let's see if I can get this up and running. I guess I can. If you have a patient or a phantom here, and you've got, let's see, this, and you've got your light field coming in here, the light field would sort of draw your borders here. That's going to be more of your geometric field size as it intercepts, or you see it on the patient. Doesn't necessarily have to be at the surface of the patient, but that's how we'll think of it for right now. The dosimetric, or the physical field size, would be related to a particular isodose line that would go out and hit these, a particular size here. This may be 50%. Could be defined as something different, but that's usually what we're looking at. Unless otherwise stated, the field size here is going to refer back to the geometric field size of the geometric borders. Also, the field size is going to be defined at a predetermined distance, such as SSD or SAD. In other words, it could be at the surface of the patient or it could be within the patient. But that's how they're going to refer to it. And generally, if we're looking at an SAD, then that latter term is the distance from the source to the axis of gantry of rotation, known as your isocenter. In other words, at isocenter, what is your field size? And that's pretty much what we're looking at. That's what we're going to set it to. So for a small field size, one may assume that the depth dose is primarily caused by the primary radiation. In other words, the photons that have traversed the overlying medium without interacting yet. The contribution of the scattered photons on the depth dose is negligibly small and may be assumed to be 0. However, you increase that field size, the contribution of the scattered photons to the absorbed dose starts to increase. The increase in the PDD caused by increase in field size depends on the beam quality. Since the scattering probability or scatter cross-section decreases with increasing energy, and the higher energy photons are scattered more predominantly in the forward direction, then the field size dependence of PDD is less pronounced for the higher energy than for the lower. PDD for radiation therapy beams are usually going to be tabulated using square fields. It's just easier to measure that way. The majority of treatments, however, are going to be irregular. And so we've got to have a way of going from these nice, neat little square fields or, circular fields or what have you, into these irregular fields. So as it turns out, we have an empirical method, nothing where this is derived from anything other than, well, it's not derived from anything other than experience, hence the meaning empirical. We use this particular formula. Now I have a summation of this that's available out there in the course, but this is how you do it. What we are looking for here is the area or the ratio of area to perimeter. So what we're going to do is we're going to attempt to figure out what an irregular field such as 10 by 20, what sort of A over P ratio are we going to be looking at? So the so what we're going to have here, let's see if I can find the formula right here, is the way to figure that out is the equivalent field parameter. So we've got A divided by P is going to be A times B, where A is the field width and B is the field length. And for square fields, if you substitute A in for B, since they're all the same size, then it reduces to this. So from these equations, we can take the side of an equivalent square field of a rectangle is going to be this. So for a 10 by 15, if we run it through this particular formula here, let's see what we end up with. Let's see, drawing. Okay, so let's see, what do we say, 10 by 15? So I'm going to assume this is the width and this is the length. So A P is going to be equal to 10 times 15 divided by 2 times the sum, 10 plus 15, I'm sorry. So that ratio, sloppily drawn as I've got it, is 150. 10 plus 15 is 25. So it's going to be 50. That equals 3. So that's where they get the AP of 3. So then the question becomes, how do we take this number and then give it this particular equivalent square? So let's take 3, which was the ratio here of A over P, and let's put it in this particular formula here for the equivalent square. Now, where did this come from? Well, it's a rearrangement of what we had up here. If we're looking at a square field, A, and we solve for that, basically we take both sides, multiply by 4, and we get this. So if we know what this ratio is, which we just figured out over here, we can then take it, put it in here, and that's where they get the equivalent square of 12 by 12. Same thing happens up here with this particular example. The A over P ends up being 3.33. You take that, you multiply it by 4, and that's where you come up with 13.3, about the 13.3. So this, again, is a way of taking an irregular field arrangement and taking it into something that is actually a square. So we'll have some examples going forward about how to do that. There's also a table here in the book that allows you to do that particular conversion. If you look up whatever the longer field size is here, cross-index that with a shorter field size over here, then you can determine what the equivalent field size happens to be. And obviously, if it's in between these two, then you'll have to do some interpolation. You'll have to sort of come halfway in between those. If it's, say, you're looking for a 19 here, 19 by 18, and you're trying to split the difference. Now, if you're looking for an equivalent circle, this is the formula, again, that you can use. All that to reiterate that, again, this is something that works empirically. It is not something that can be derived from something else. It just happens to work out that way. So, pardon me. The dependence on source to surface distance. What we are looking to do here, we know that the photon fluence emitted by a point source of radiation varies inversely as the square of the distance from the source. In other words, it falls off according to the inverse square law. We have chosen the SSD to be large or something greater than 80 centimeters so that the source dimensions become unimportant in relation to the variation of the photon fluence with distance. In other words, it can be considered as a point at large SSD. So the exposure rate or the dose in free space from such a source varies inversely as the square of the distance. The percent depth dose increases with SSD as a result of the inverse square law. In other words, the further away that you get, and again, this may sound a little counterintuitive, but the further away you get, the higher the PDDs actually become. And that's relative to where they were if you actually moved in closer to the source. So although the actual dose rate at a point decreases with increase in distance, then the PDD, which is a relative dose with respect to a reference point, increases with SSD. So in clinical radiation therapy, this is obviously an important parameter. Because PDD determines how much dose can be delivered at depth relative to D max. It needs to be as large as possible. But since the dose rate decreases with distance, the SSD in practical is set at a distance that sort of provides a compromise between the dose rate and the PDD. That's why it's generally set where it is. So tables of percent depth dose for clinical use are usually measured at a standard SSD. Usually it's 100 centimeters for Linex beams. We're not really that concerned for cobalts. So in a given clinical situation, however, the SSDs are set on a patient and they may be different from the standard SSD. You may require a larger SSD that involves field sizes larger than the ones that are available at a standard SSD. One of the things that you may have already done at this point is to do an extended SSD treatment for, say, a femur, where you can't get a femur in at using a regular Ssd treatment because the femur is just too long. You can't get it completely exposed unless you move the patient further away from the machine, at which point you might be able to get it all in there. So sometimes that does happen. Now, you have more accurate methods available to be able to make this type of adjustment, but one approximation that we're going to go through here is called the Maynard F Factor. This method is based on a strict application of the inverse square law without considering changes like scattering as the SSD changes. So figure 9.6 here is kind of showing what's going on. So we've got our Dmax here, we've got our percent, we've got our depth dose in the phantom. We want to keep the same field size here and the same depth, but again, we can't cover what we need to, so we're going to back or move the phantom away or move the patient away from the treatment unit. And so our result is going from what you see in situation A there to what you see in situation B. So the SSD in part B is going to be different from what we have in part A. How do we do that? How do we address that? And this is where they're talking about the Maynard F Factor. So we know that the variation in dose with depth is going to be governed by three effects. It's going to be the inverse square law, exponential attenuation, which is going to be this term, and the scattering, which is going to be this term. So this is the inverse square law. This is the exponential attenuation, and this is going to be the scattering. This is all part of the PDD. Again, mu here is going to be the linear attenuation coefficient for the primary beam, and this is going to be the change in the scatter dose. So ignoring the change in the value of K from one SSD to the next, and another note about mathematics, this is going to be the percent depth dose. That's what the P is going to stand for here. All of the stuff in parentheses here are going to be the things that influence that. It's going to be the depth of the treatment. It's going to be the size of the field size there at in this particular case at the surface. And this is going to be the SSD at that particular point. So you can see how all of those factors are placed in here. If we change the SSD up, but leave all of these other things the same, this is how that same formula is going to change. This is not going to change. This is not going to change, but this factor will. If we make a ratio of this over this, what we're going to find out is that these terms and these terms cancel with each other. And because they end up canceling with each other, when we do the ratio here, this is all that's going to be left. And the ratio of one SSD over the other is going to be defined as this, and this F is going to be written in its place, and this is going to be considered the Maynard F factor. So the F factor is going to be greater for 1 if F of 2 is greater than F of 1, and less than 1 if F of 2 is less than F of 1. So the PDD increases with increases in SSD. So let's go through this particular example here. Let me see if I can include all of this in it. So example 1, the PDD for a 15 by 15 field size at a 10 cm depth and 80 cm SSD is 58.4. That's the PDD for a cobalt 60 beam. So what is the PDD for the same field size and depth for a 100 centimeter SSD? All right, so we're going to take this particular equation and we're going to figure out what the PDD is going to be. To get that, we're going to need the Maynard F factor. So we know that our new SSD is going to be 100, so we put that in place of F2. That's where that goes. Here, the D sub max is going to be 0.5. That's what it's going to be for Cobalt 60. The F of 1 is going to be what we were originally at, which is 80 cm SSD right there. So we put F of 1 again is going to be here. The depth that we are interested in again is a 10 cm depth. I'm going to put that in here. The new SSD is going to be 100, and that's going to be placed here. And then D again is going to be 10. So if you go through the computations here, you're going to add those two together and then add those two together, and you're going to divide. And once you do that, then you apply the exponent on the outside. Same thing is going to be here. You're going to add the 80 to the 10, which is going to be 90. You got 100 plus 10, that's going to be 110. So you got 90 divided by 110. And then you take that ratio and you square it. When you multiply those two together, you end up with 1.043. So again, from this particular equation, we know that our ratio here, and if we fill in the numbers 10, 15, 100, this 10 is from the depth, this 15 is because it's a 15 by 15 field, and the 100 is going to be what we are curious to find out about. It's the second SSD divided by the PDD for 10, 15, and 80. We know that that ratio ends up being 1.043 because that's what we just figured out using this right here. So now that we know that, we know this PDD down here because it was given to us already. It's right there. PDD for this particular situation of 58.4. So we take this, move it over to this side of the equation. And so this value is going to be equal to this, which we already know is 58.4 multiplied by the Maynard F factor. We end up with 60.9. So this is the PDD at that particular SSD, with all of the other factors remaining the same. Now, again, there are a bunch of other factors that need to be taken into account, but this is a pretty good, quick and dirty estimation as to what the change is going to be like. Works well for small fields since the scattering is minimal. However, it can give rise to significant errors if you have a low energy, a large field, large depth, large SSD change. So if you go from at a 20 cm depth for 30 by 30 field at 160 SSD, I don't know of anybody that's ever capable of using that, but if you did, you're going to be looking at about an error of 3% if the PDD is calculated from 80 cm SSD tables. So in general, that factor is going to overestimate the increase in PDD with increase in SSD. Sometimes in order to be able to apply it more rapid or more accurately, you're going to be looking at using factors somewhere in between this particular value and the F Maynard factor, or maybe this factor itself. So that is one method. Another method is going to be the tissue error ratio. So the TAR is first introduced by Johns in 1953, originally called tumor to error ratio. At the time, this quantity was identified specifically for rotational therapy calculations. For rotational therapy, like ARCs, the radiation source moves in a circle around the axis of rotation, which is usually placed right inside the tumor, and that really hasn't changed that much. Although the SSD may vary depending on the shape of the surface contour, the SAD remains constant. So since the PDD depends on the SSD correction of the PDD will be applied to correct for the varying SSD. You can't really do that with our technology today, not manually. That's asking way too much. So a simpler quantity named TAR has been defined to remove the SSD dependence. That way we don't have to go that way. So since the time of its introduction, the concept of TAR has been refined to facilitate calculations not only for rotation therapy, but also for stationary isocentric techniques as well as irregular fields. So the TAR is going to depend on your field size and your depth. Again, we're trying to get away from having to have the SSD in there, and this is what's helping to achieve that. So this is the dose at a given point, and this is the dose in free space at some at whatever that same point happens to be. So you can see here sort of what's going on. You've got our situation here where you've got some sort of field size here at both of those, and then you've got the depth at which this is being calculated. You can get the same thing here if you've got some sort of mass here to be able to build things up. This is what the dose would be in free space. And so now you've got the TAR is defined as the ratio between what you measure here and what you measure here. In all of those computations, you don't have to worry about the SSD anymore. So again, the most important property for the TAR or tissue to area ratio is that it's independent of the distance from the source. It is an approximation that is usually valid to an accuracy of better than 2% over the range of distances used clinically. Because the TAR is a ratio of two doses at the same point, the distance dependence of the photon fluence is removed. So it represents a modification of the dose at a point owing only to the attenuation and scattering of the beam in a phantom compared with the dose at the same point in a mini phantom or equilibrium phantom placed in free air. Since the primary beam is attenuated exponentially with depth, the TAR for the primary beam is only a function of depth and not of SSD. The case of the scatter component is not obvious. However, it's been shown that the fractional scatter contribution to the depth dose is almost independent of the divergence, dependent only on the depth and the field size at that depth. So therefore, for both the primary and the scattering component of the depth dose, it's independent of the source distance. So the TAR is going to vary with energy, depth, and field size, very much like the PDD. For megavoltage beams, the TAR builds up to a maximum at a depth of maximum dose and then decreases with depth more or less exponentially. For the narrow beam, 0 by 0 field size, the TAR beyond DM varies approximately exponentially with depth. So you can see that decrease there. And this is going to be the average attenuation coefficient. As the field size is increased, scatter component of the dose increases and the variation of TAR with depth becomes more complex. With high energy megavoltage beams for which the scatter is minimal and is directed more or less in the forward direction, TAR variation with depth can still be approximated by an exponential function, provided an effective attenuation for the given field size is used. Now, the term backscatter, which is going to be next, or peak scatter factor, is simply the TAR at a reference depth of maximum dose on the central axis. It can be defined as a ratio of the dose on the central axis as a reference depth of maximum dose to the dose at the same point in free space. So in other words, basically what you're doing is, rather than just looking for some depth here, we're going to replace that with the dose at the maximum depth. And this is another way to symbolize that. This is going to be the field size at that reference depth. This is going to be independent of the distance from the source and depends only on the beam quality and the field size. So you can see here the backscatter factors for various quality beams and field areas. Whereas the BSF increases with field size, its maximum value occurs for beams having a half value layer between 0.6 and 0.8 millimeters of copper, depending on the field size. Thus, for an orthovoltage beam with usual filtration, the BSF can be as high as 1.5 for large fields. That can be quite a bit. So for megavoltage beams, the backscatter factor is much smaller. For example, the BSF for a 10 by 10 is about 1.036. So rather than being up close to 50%, in some cases now it is much, much lower. And if you're above 8 MV, then the scatter at the depth of Dmax becomes negligibly small, and that becomes its minimal value of unity. So depending on what energy of beam you're using here, your backscatter factor can be fairly significant. But as you get to higher energy beams, it becomes closer to unity. So now, how does one go about relating TAR and percent depth dose? You can kind of see the relationship here, where you can see where you've got here in this particular situation, you've got a certain reference depth that you're looking at here. You've got your Dmax at this particular point, and then you're actually interested in a point here. So you can see the measurement in air, the dose at free space at this point, and the dose in free space at this point. So you can see how these two can be related. You see how these two can be related. Both of these are TAR measurements that you can make. You know that this point is related to this point through a PDD. So if you want to be able to relate all of these points, all you have to do is put together everything you know. So let D sub Fs of P and D sub Fs of Q be the doses in free space at points P and Q. In other words, this and this. If we put those together there, these are related by the inverse square law. In other words, the only effect that you're going to see between those two that's going to change it is going to be the change there in the distance between the two, those 2 points. In other words, this distance right here. That's just going to follow the inverse square law. The field sizes are going to be related as follows. In other words, the field size at your reference point D and field size at R is going to be related through this relationship. We all know that the TAR, which we just defined, is going to be the dose at some point D divided by that same dose in free space. We can rearrange that here to solve for this. Put that here and that here. We know that the Dmax for P, since that's how it's defined here, that's Dmax. We know that the Dmax here divided by that same point in free space is going to be referred to as the backscatter factor, because we know that backscatter factor, that's how it's defined, is related to the point at Dmax. If you go back and you check this particular formula, you can see that. So from all of that, we know here that the dose at a particular point with all of these other factors, and that percent depth dose is equal to this. And therefore we can go through and we can start substituting in the things that we know. We know that this can go in for this particular value. We know this can be substituted in for this particular value. And once we get all of those put together there, we know that the TAR is involved. We know the backscatter factor is involved. We know that this ratio is involved. Again, that ratio comes from here, and we can substitute that in. So now we have just related the PDD, the TAR, the backscatter factor, and the inverse square law. All of that's related right there. 9.23. So conversion of percent depth dose from one source to surface distance to another, the tissue, the TAR method. So let's say here, suppose F sub 1 is the SSD for which the PDD is known, and F sub 2 is the SSD for which the PDD is to be determined. In other words, we don't know what that PDD is. R is going to be the field size at the surface, and D is going to be the depth for both cases. So referring back here, then R sub D F1 and R sub D F2 be the field sizes projected at depth D. So from the equation that we built before and the fact that we're looking at two different SSDs, all we have to do is go through and change F1 and then F2. The conversion factor here for PDDs is basically going to be the ratio of these two. And then as we go through, we can also, the TAR method is going to correct the Maynard F factor by the ratio of the TARs for the fields projected at the two SSDs. So to convert one to the other, there's this particular formula. There's also the Maynard factor here. So again, this is another method by which you can convert one PDD to another. So now we're going to go through some practical examples here of how all of these particular methods can be roped together into one problem. And actually, there's going to be several of these, so just sit tight, hang on. All right, for example 2 here, you've got a patient that's going to be treated with an orthovoltage beam having a half value layer of 3 millimeters of copper. Suppose that the machine is calibrated in terms of exposure rate in air. We're going to find the time required to deliver 200 centigrade at 5 cm depth given the following data. You've got the exposure rate, you've got the field size, you've got the SSD, you've got PDD, you've got backscatter factor, and the centigrade to Rankine ratio here is 0.95. So you have the dose in free space is going to be equal to the exposure times the rad to R factor times equivalent area, which the equivalent area in this particular case is just going to end up being 1. There's no real change here. The exposure rate is 100 Rankine per minute. The amount of centigrade per Rankine is going to be 0.95 multiplied by that. So we know that the dose rate in free space is going to be 95 centigrade per minute. And again, what we are looking for here is the time required to deliver 200 centigrade. So we have to have some time element in here, and we know what the dose rate is in free space. So we'll eventually get to the time. If we're looking for the dose rate at D max, we're going to take the dose rate that we have here at this particular point, and we're going to multiply it by the backscatter factor. So when we do that, we know the backscatter factor here, it's given to us, it's 1.20. Then when we do the multiplication here at D max, we are looking at 114 centigrade per minute. The tumor dose that we want to deliver here is going to be 200 centigrade. So D max to be delivered is going to be the tumor dose divided by the percent depth dose multiplied by 100. So we're going to take the tumor dose, which here is going to be 200 divided by the percent depth dose, multiply it by 100, and it ends up being 308.6 centigrade. The treatment time is going to end up being the D max dose to be delivered and divided by the rate at of course, Dmax. So we have 308.6 centigrade. It is delivering 114 centigrade per minute. We do that, and it comes out to be 2.71 minutes. So again, we know what the dose being delivered is at a particular point in space. What we are attempting to do is to, of course, set up the delivery of 200 centigrade to be at the maximum, or a Dmax. And so what we're looking for is a way to be able to take that dose rate information at Dmax and try to figure out exactly how much time we're going to need, since it's calibrated. The machine is calibrated in terms of exposure rate and error. We're trying to figure out what that amount of time needs to be in order to be able to deliver that amount of dose. So example 3, a patient is to be treated with cobalt-60 radiation. So supposing that the machine is calibrated in error in terms of dose rate free space, find the treatment time to deliver 200 centigrade at a depth of 8 cm given the following data. So we know the dose rate in free space is 150 centigrade per minute at 80.5, because that's where the maximum is going to end up being. For a field size of 10 by 10, SSD is 80, PDD is 64.1, the backscatter factor is 1.036. So the Dmax rate is going to end up being a 150. We know what the backscatter factor is, so it ends up being 155.4 centigrade per minute. The Dmax is going to be 200 divided by the PDD at the depth that we're looking at, multiply by 100, of course, because this is supposed to be a percent. And we end up being 312 centigrade. And we take 312 centigrade and we divide that by the dose rate at the maximum, and we end up with 2.01 minutes. So example 4, during the time required to deliver 200 centigrade with a cobalt-60 gamma ray beam at the isocenter, which is placed at 10 cm depth in a patient, given the following data. SAD is 80, field size is this, dose rate at free space at the SAD is going to be this, and the TAR is 0.681. Since we have an irregular field here, or a rectangular field, we're going to take that and try to figure out what the equivalent square field is going to be. So A over P for 6 times 12 cm squared field. Again, we go through that formula that we saw early on, and it ends up being a ratio of 2. So the side of the equivalent square field is going to be 4 times that, which is going to be 8 cm. The TAR for this is going to end up being 0.681. We know that because the TAR, given the depth that we want to go, and now we know what the equivalent field size is. We know what the given dose is going to be, or what we want to deliver here is 200 centigrade. The TAR is going to be the dose that we want to deliver divided by the dose in free space. So we take 200, which is what we want to deliver, and we know what that TAR ratio is because it's given to us. So the dose in free space, if we solve this formula for D sub Fs, put it over here, the TAR goes down here. So we end up with this. And so the dose in free space rate is given to us right here, 120 centigrade per minute. So the amount of treatment time that we're going to need is going to be the dose in free space divided by the rate. And so we end up with 2.45 minutes. Now, The concept of the TARs is going to be most useful for calculations involving isocentric techniques of irradiation. Rotation, and believe me, today you're going to be seeing more and more arcs around. Arcs are a very good way in order for you to be able to deliver a lot of dose into a very centralized area. It's also a great way to increase your integral dose, but sometimes those are the kinds of trade-offs that you have to make. In order to be able to try to figure out what the average TAR is at the ISO center, sometimes we're going to have to take a patient here and we're going to have to evaluate what the TAR is at several different sectors as you make an arc rotation all the way around. And anytime you see a bar like this over a value like that, it denotes an average. So we're going to be looking for an average TAR. So here's an example for the data given in table 9.3, which is what we've got here. We're going to determine the treatment time to deliver 200 centigrade at the center of rotation given the following data. The dose rate in free space for 6x6 cm field of the Ssd is 86.5 centigrade per minute. So if we take all of these particular angles as they're measured, and we find out what the TARs are, and we go through and we do an average, we find out that the average, if we add all of those together, divided by the number that's in there, it comes up with 0.538. Again, the field size is going to be a 6x6. The dose to be delivered at isocenter, we know what that is, usually around 200 centigrade. Dose free space to be delivered at isocenter is going to be 200 divided by 0.538. This is the dose that needs to be delivered. We know what the dose rate in free space happens to be. This is the dose that will be delivered at the isocenter in free space. We know what the rate is. If we take the amount divided by the rate, this is how long the machine has to be on. Now, as if you needed another acronym to worry about, the scatter error ratio is used for the purpose of calculating scattered dose in the medium. The computation of the primary and the scattered dose separately is particularly useful in the dosimetry of irregular fields, and we'll have some examples over this. So the scatter error ratio at a particular depth with a particular reference field size is going to be the tissue error ratio minus the tissue error ratio for the primary beam. This is going to be used in calculating scatter in a particular field shape. These are tabulated as functions of depth and radius for a particular circular field. Because the SAR data are derived from TAR data for rectangular square fields, the radii of equivalent circles may be obtained from certain equations. So this is supposed to be a Mantle field. So we're going to expose all of the stuff that's in the white, and we're going to try to block the part of the windpipe here and try to block the lungs. Again, this is an old picture. You would never do this pretty much anymore in the modern day, but there we are. So this is a treatment for Hodgkin's disease. Since a lot of this is available for rectangular fields, methods are required to use data for general cases of irregularly shaped fields. What we are wanting to do with the Clarkson method is to determine what the average SAR happens to be. And as you're going through, what you're attempting to do is you're trying to figure out what the scatter error ratio is for all of these particular angles as you're coming in. You come up with an average SAR for an irregular field at point Q, the point at which we are measuring, that's point Q right there. And so for sectors passing through a blocked area, like some of these beams are coming straight in and there's nothing there to block them. But some of these beams are actually coming through in areas where you are seeing some block that's in the way. How do you deal with that? Well, let's take this particular beam here, right here, number 5, as it's coming through. As it's coming through, this area is not blocked, this area is, and then this area is no longer blocked. What you're going to do is, in trying to figure out what the SAR is for that particular part of the sector, if you're looking for from Q up to C, whatever that SAR happens to be, that SAR minus the blocked area minus the unblocked area. So the SAR from here to here is pretty much going to be from here to here minus whatever it is from here to here, and then adding back in whatever it is from here to here. So there's going to be a lot going on with that. And the subtraction is actually going to be, we'll add in what goes from here to here, we'll subtract whatever that value is from here to here, and then we'll add back in that ratio again from here all the way out to here. That's a lot of addition and subtraction going on there. But once we figure out what this average scatter error ratio is, we can determine what an average TAR is through this particular formula. Again, we've got the TAR of the primary beam plus the average of the scatters that comes in through all of the different angles. And again, the TAR for the primary beam, we're just looking at the average linear attenuation coefficient here for that particular beam. The percent depth dose at Q may be calculated to D max on the central axis using that big long equation 9.23 that we came up with. And the backscatter is going to be from the irregular field as calculated by the Clarkson's method. This is going to be something that we will have an example on later on. It's not something I would ever see any of you actually doing in the clinic, but it's very good to know going forward how this is put together, and a little bit of experience on this would be good. The summary here goes over a lot of the key points that I tried to illuminate here. I would very much encourage you to go through that. I will have some homework out later on, and I will have some videos over examples here that I think would be useful for you. So I hope this was illuminating to some degree.